This lesson is on solving equilibrium problems using the rights table. Solving problems involving the determination of equilibrium concentration of a system at various conditions can be a challenge. For this lesson, we will examine the following for various problems. 1. A rights table. 2. Methods to solve the equilibrium concentration. A. Approximation. B. Method of successive approximation. C. Quadratic equation. A rights table stands for reaction, initial concentration, change in concentration, and equilibrium concentration. For any equilibrium problem, you must have at minimum the following. 1. Reaction equilibrium. 2. Table containing the following shown to the right. 3. Equilibrium constant of the system is applicable. 4. A calculator, especially one that can do quadratic or cubic root calculations. Here before you are some scientific calculators that cannot solve for quadratic or cubic root calculations. Scientific calculators include TI 30XA and Casio FX 300ES. In order to solve these problems by formula, you have to manually do them. Here before you are some scientific calculators that can solve quadratic and cubic root calculations. Scientific calculators include Casio 991EX and TI 36X Pro. We will go over the most common types of equilibrium problems one might encounter. While this will not cover all types, the hope is you'll be more comfortable with being able to solve chemical equilibrium problems. The first case is where one is given an equilibrium constant and the initial concentration of a substance. The method to solve for the final equilibrium concentrations is by the approximation method. The problem is to determine the final equilibrium concentrations for all species in a 0.500 m HF aqueous solution. K equals 6.8 times 10 to the minus 4. The balanced chemical equation is HF in equilibrium forms H plus and F minus. Step 1 is to create the rights table and fill in the initial conditions. The initial concentration of HF is 0.500 molar, where H plus and F minus are both 0. Step 2 is to fill in the change row by determining which substance will decrease in concentration and which will increase in concentration. In this reaction, HF's change is minus X, and for both H plus and F minus, the change is plus X. Step 3 is to fill in the equilibrium concentration row by subtracting the change concentration from the initial concentration. The equilibrium concentration of HF is 0.500 minus X, and for both H plus and F minus, their equilibrium concentrations are X. Step 4 is to use the equilibrium expression and equilibrium constant to solve for X. Ka equals 6.8 times 10 to the minus 4, which equals the concentration of H plus times F minus over the concentration of HF. In filling their equilibrium concentrations in, it is revised as 6.8 times 10 to the minus 4 equals X squared over 0.500 minus X. If you assume X is small, you must compare the original concentration against its K value. And if it is at least greater than or equal to 400, the assumption is valid. If we take the initial concentration of HF and divide it by its K value or equilibrium constant value, it equals 735, which is greater than or equal to 400. So the assumption that X is valid is confirmed, and thus X is small. The revised equation is 6.8 times 10 to the minus 4 equals X squared over 0.500. It expands to X squared equals 0.500 times 6.8 times 10 to the minus 4. Solving for X equals plus or minus 0.018 m. only the positive is considered. The equilibrium concentration of H plus and F minus equals 0.018 m, and the equilibrium concentration of HF equals 0.500 m minus 0.018 m equals 0.482 m. Case 2 is where one is given the equilibrium constant and initial concentration of one or more substances. The method is called the perfect root method. Consider the reaction COG plus H2OG at equilibrium forms CO2G plus H2G. Kc equals 102 at 500 Kelvin units. If a reaction mixture initially contains 0.100 m CO and 0.100 m H2O, what will the equilibrium concentration of each of the reactants and products be? One writes out the equilibrium equation and also in step 1. Create the Rice table and fill in the initial conditions. The initial conditions of CO and H2O are 0.100 molar, whereas for CO2 and H2, it is 0. Step 2 is to fill in the change. The change for CO and H2O are both minus X, and for CO2 and H2, plus X. Step 3 is to fill in the equilibrium concentrations row by subtracting the change concentration from the initial concentration. The equilibrium concentration for CO and H2O are 0.100 minus X, and for CO2 and H2, they are X each. Step 4 is to use the equilibrium expression and equilibrium constant to solve for X. In this case, Kc equals 102, which equals X squared divided by 0.100 minus X quantity squared. If the concentration and equilibrium for the reactants and products are identical and are raised to the same exponent, one can take the inverse root to that exponent. In this example, shown, if we take the square root on both sides, after some rearranging in solving for X, we will only be solving for the positive, which in this case, X equals 0.0910. The equilibrium concentrations for CO2 and H2 both equal 0.0910 m, and for CO and H2O, their equilibrium concentrations are both 0.009 m. Case 3 is on given an equilibrium constant and initial concentration of a substance, use successive approximation method . The problem is Hc2H3O2, Aq plus H2L at equilibrium forms H3O plus C2H3O2 minus. Where Ka equals 1.8 times 10 minus 5. If a solution initially contains 0.00200 m Hc2H3O2, what is the equilibrium concentration of H3O plus? Step 1 is, after writing the chemical reaction, is to create the Rice table and fill in the initial conditions. In this case, the initial conditions are as follows. Hc2H3O2 has an initial concentration of 0.00200 molar, and H plus and C2H3O2 minus has initial concentrations of 0 each. Step 2 is to fill in the change row by determining which substance will decrease in concentration and which will increase in concentration. In this case, Hc2H3O2 has a change of minus x, and for H plus and C2H3O2 minus, they are both x. Step 3 is to fill in the equilibrium concentrations row by subtracting the change concentration from the initial concentration. And after doing that, the equilibrium concentrations are 0.00200 minus x for Hc2H3O2, and for H plus and C2H3O2 minus, both have an equilibrium concentration of x. To determine if x is small, we take the initial concentration of acetic acid, or Hc2H3O2, and divide by K value to determine if x is small enough to ignore. If one takes 0.00200 and divide by 1.8 times 10 minus 5, the answer is 111, which is less than 400. Step 4 is to determine under successive approximation the final value of x. The equilibrium expression is K equals 1.10 to the minus 5 equals the concentrations of H plus times C2H3O2 minus divided by the concentration of Hc2H3O2 equals x squared divided by 0.00200 minus x. The first calculation is done by undergoing the first assumption not from the initial concentration of the reactant is 0. It is rewritten as the following. 1.8 times 10 to the minus 5 equals x1 squared divided by 0.00200. x1 equals 0.00019 m. One continues this process until the last two values are equal. Provide the value in the previous assumption calculated and subtract it from the initial concentration of the reactant. For the second assumption, with x1 equals 0.00019 m, if we plug in the value and subtract from 0.00200 and perform the same calculation, x2 equals 0.00018 m. Again, this process continues until the last two values are equal. Provide the value in the previous assumption calculated and subtract it from the initial concentration of the reactant. For the second assumption, with x2 equaling 0.00018 m, if we plug in the value and subtract it from 0.00200 and perform the same calculation, x3 equals 0.00018 m. As one can see, x2 and x3 are the same, so this process is over. The equilibrium concentration of H plus equals C2H3O2 minus, or 0.00018 m, and for Hc2H3O2, the equilibrium concentration is 0.00200 minus 0.00018, or 0.00182 m. Case 4 is one is given the equilibrium constant and initial concentration for a substance. The method used to solve for x is the quadratic equation. The problem is determine the equilibrium concentrations for all species in a 0.250 m HF aqueous solution. Determine the pH of this solution. Ka equals 6.8 times 10 to the minus 4. Note, for this exercise, the pH of this will not be solved. Step 1 is to create the Rice table and fill in the initial conditions. The initial concentrations for HF is 0.250 molar, and for H plus and F minus, it is 0 each. Step 2 is to fill in the change row by determining which substance will decrease in concentration and which will increase in concentration. The change for HF is minus X, and for H plus and F minus, they are plus X. Step 3 is to fill in the equilibrium concentration row by subtracting the change concentration from the initial concentration. The equilibrium concentration for HF is 0.250 minus X, and X for both H plus and F minus as their equilibrium concentrations. If you assume X is small, you must compare the original concentration against its K value. And if it is at least 400, the assumption is valid. In this case, the ratio equals 368, and since it is less than 400, the assumption X is small is invalid. You have to solve for X either by successive approximation or by the quadratic equation. Under the quadratic method, we rewrite the equation as a second order polynomial where 0 equals ax squared plus bx plus c, and use the quadratic equation to solve for x. The quadratic equation is x equals minus b plus or minus the square root of b squared minus 4ac divided by 2a. After expanding the Ka expression in the form of the quadratic equation, one plugs in the values of a, b, and c, where a equals 1, b equals 6.8 times 10 minus 4, and c equals negative 1.7 times 10 minus 4. X equals 0.0127 or negative 0.0134. In this situation, since we have a positive and negative root answer, only the positive root is considered. If the values for x are both positive, select the positive that when subtracted from the initial concentration of reactant or product, it results in a positive value. The equilibrium concentration of H plus and F minus are 0.0127 molar each, and for HF, the equilibrium concentration is 0.237 molar. Case 5 is where an initial concentration of one or more substances and at least one substance concentration at equilibrium is provided. Solve for K. Consider the reaction Fe3 plus AQ plus SCN minus AQ at equilibrium forms FeSCN2 plus. A solution is made containing an initial concentration of Fe3 plus equals 0.00010 m and an initial concentration of SCN minus of 0.0000080 or 8.0 times 10 minus 5. At equilibrium, the concentration of FeSCN2 plus equals 0.000017 m. Calculate the value of the equilibrium constant, Kc. Note Kc means equilibrium constant in terms of concentration. Step 1 is to create the Rice table and fill in the initial conditions. The initial concentrations of Fe3 plus and SCN minus are 0.000100 molar and 8 times 10 to the minus 5 molar respectively. The initial concentration of FeSCN2 plus is 0. Step 2 is to fill in the change rule by determining which substance will decrease concentration and which will increase concentration. The change in concentration for both Fe3 plus and SCN minus are minus X, and for FeSCN2 plus, it is plus X. Step 3 is to fill in the equilibrium concentration, if any, is provided and solve for X. In this case, with the equilibrium concentration of FeSCN2 plus is 0.000017 molar. The equilibrium concentration of both Fe3 plus and SCN minus are in question. Step 4 is to solve for the final concentration of all other species. FeSCN2 plus equals 0.000017 molar, or X. Fe3 plus equals 8.3 times 10 to the minus 5 molar, and SCN minus equals 6.3 times 10 to the minus 5 molar. Step 5 is to solve for the equilibrium constant of the system using the equilibrium concentration of all species. KEQ equals the concentration of FeSCN2 plus divided by the concentrations of Fe3 plus times SCN minus. KEQ equals, after plugging in the equilibrium concentrations, 3.25 times 10 to the 3.